In this lesson, we're going to learn about the transformations of curves. And before we talk about transforming or changing curves, we want to first just establish a certain collection, or maybe you can call it a library of graphs and their associated functions. So the first one should be familiar to you. Again, if we think of f of x as being y equals x is a straight line with a slope of 1 and a y-intercept of 0. Next, the graph f of x is equal to x squared, or y is equal to x squared. That's our basic parabola. And for each of these graphs, you can plot them yourself by plotting points and connecting the dots, but we won't go through the details of that. So one of the purposes of transformations is to speed the process of graphing, and so we're actually going to avoid plotting points one at a time. For our third graph, we have y is equal to x cubed, and so that's our S curve that rises rapidly. F of x is equal to x to the fourth is rather similar to a parabola, but it rises even more quickly than the parabola does. It does also pass through the origin and the points -1, 1, and also +1. If you think of substituting x is equal to 1 or x is equal to +1 raised to the fourth power, we will still get the ones, but again, rising more steeply than on the parabola. For the absolute value graph, when x is positive, we just have the line y equals x, identical to this. But when x is negative, we are going to take the opposite of x. That is that whenever the x comes out negative, we're going to flip it or reverse it and make it positive. F of x is equal to 1 over x is the reciprocal graph. And these two are actually very closely related, number 7 and 8. So let's look at this one first. X is equal to y squared. If you were to switch the coordinates and make it y is equal to x squared, that would be our standard parabola through the origin. And so when we exchange y for x and x for y, we can see then that we could flip these two axes, the x-axis and the y-axis, and so instead of opening upwards, this graph is going to open sideways. And this is actually not a function. Again, it fails the vertical line test, but it is a graph, and if we want to define it as a function, what we can do is to choose only to use the positive arm of this function. So if we were to solve this for y, we could take the square root and say then that y is equal to, and because it's a square here, we would have to say that y would be equal to either positive or negative square root of x. And so again, we can say that by taking the positive arm only, this will define a function. Next, now that we have shown you some basic functions, we would like to do some manipulations or changes on these functions. And one of the very important things when we change the function is to realize what the important landmarks on each graph are. So in this case, with the line y equals x, this line passes through the origin, and so the y-intercept at the origin is very important. Here, the vertex is very important for x squared, and for x to the third power, this turnaround point where it looks like at first it's facing downward and then it changes direction and looks like it's facing upward. We call this an inflection point, and that inflection point is again the origin. For f of x is equal to x to the fourth, the vertex is the origin. For f of x is equal to the absolute value of x, the point of the v again is the origin. And for the reciprocal graph, we don't really have a vertex, but if we were to think of where the center of this graph is, the center is again at the origin. So if we draw the x and y axes, these axes are kind of the guiding lines, sometimes what we call asymptotes, for the arms of this reciprocal function. For number 7 and 8, the vertex on number 8 is the origin, and for number 7, the starting point where we begin to draw this arm that goes up is again the origin. So the origin is a very important point for our basic graph, and we will then again do manipulations on these basic graphs. The first transformation we're going to do is vertical translation. And when you take a look at a function like f of x is equal to x cubed plus 3, we can identify our basic function or our basic graph as being y is equal to x cubed. And so the first thing I'm going to do is draw that basic graph. And the graph that I've drawn in pink isn't exactly the graph that we're given. It's the basic graph of f of x is just equal to x cubed. However, there's a lot of similarity between the function that we've been given and the basic graph that we were given before that we should be memorizing. So when you take a look at this plus 3, what it does for us is it adds 3 units to every point. And so if I were to take this origin point and add 3 to the y value, I'm going to get a new point at 0, 3. And that new point at 0, 3 is the important landmark of the origin, which has been shifted up, which means that every other point is going to be shifted similarly in relation to that. So the point 1, 1 will also be shifted up 3 units and appear here. And the point negative 1 will be shifted up through 3 units and appear here. And so our new graph will appear very similar to what you see with the blue line. This is what f of x is equal to x cubed plus 3 should be looking like. And again, it's very similar to the original function x cubed, but shifted up by only 3 units. We can do something very similar over here with the function f of x is equal to x cubed minus 2. So we'll start with our basic graph, x cubed. This time, for x cubed minus 2, we're going to take that landmark at the origin, and instead of shifting it up 3 units as we did before, we're going to shift it down by 2 units. And the graph will appear something like this. So vertical translation is fairly straightforward. That basically, if we add a certain constant or number to the outside of the function, we will shift it up, and if we subtract a certain constant or number, we will shift it down by that number of units. In contrast, horizontal translation is going to happen when you have a number which is added or subtracted from the inside of the function. So in example B, we see that the basic function here is x to the 4th power, or a 4th powered function, but the adding and subtracting is done not to the outside, out here, but on the inside, very close to the x. And so we see here that f of x minus h, with again the x minus the number inside the parentheses, is going to shift our basic graph right by a certain number of units. So starting with the x to the 4th power function, it's going to look like this. And then we're going to take that function and shift it to the right so that it looks something like this. And notice that the landmark that we can use to decide where we're going to shift is the origin, so we shift from the origin to the point 2, 0. Now, some of you might not be convinced that this should shift to the right, and so if you're not sure if this is correct, you can actually go back and plot some points here. So for example, if I were to let x equal 2, I can plug 2 in this equation, and 2 minus 2 is 0 to the 4th, which is equal to 0. If I wanted to test out another point, for example, when x is equal to 1, I get that 1 minus 2 is equal to negative 1, so 1 minus 2 is negative 1, raised to the 4th power, and that's equal to positive 1. So you can see when x is equal to 1, f of x is positive 1, and if I wanted to go all the way back to 0, I would get a rather large number, but I would get 0 minus 2 is negative 2, and when I raise that to the 4th power, I get 16. And this line, or the edge of that blue curve, goes as it gets closer and closer to 0, you can see that it's rising rather rapidly, but we can anticipate that it would hit the axis at y is equal to 16. Similarly, we can get a horizontal translation by adding to the x value inside the parentheses. So again, this is not outside the function over here, but it's on the inside of that fourth power. And this time, we are going to see that this will shift left by that number of units, that is by 1 unit. So when we start off with our basic graph, this time the action of adding 1 should take this graph and shift it to the left by 1 unit. And so again, our landmark is at the origin, and it's going to shift to the point -1, 0. So we can see that it shifts left. If you're not fully convinced of this, again, you can test it out by plotting some points. And if I were to check out when x is equal to a -1, I can plug that into the equation. -1 plus 1 is 0, and you raise that to the fourth power and you get 0. And so we do have the point at -1, 0.